Planning for Florida's transportation future starts today. Predicting future travel needs, including who is traveling, where they are going, and how they get there, enables transportation professionals to make more informed decisions around long-term investments. This is a video in a series on travel demand modeling. All of the videos can be found on Florida's Transportation Forecasting Resource Hub at www.fdot.gov/forecasting. Travel demand models are mathematical models that use inputs like population data, land use characteristics, and transportation network to make estimations on the existing travel patterns and predictions about future travel conditions. This information can be used to evaluate transportation solutions or investments, as well as inform policies for future transportation and land use development. The type and accuracy of data inputs are critical to producing trusted and context-relevant results. There are three categories of data typically used by the travel demand model: land use data, transportation network data, and travel data. Land use data. The travel needs of a suburban residential area are likely to be different than those in a city's downtown with a large employment center. Land use data helps answer the question of who is traveling within an area and where they may want to go. Key inputs to the model include land use types and intensity, such as household size, number of service employees, number of hotel rooms, school enrollment, or income and age distributions within an area. Different data sources for these inputs include the U.S. Census Bureau, Bureau of Labor Statistics, Bureau of Transportation Statistics, and national or local household travel surveys. Different trip rates are applied to different land use types and trip purposes. The people and place data are stored in small geographic units as traffic analysis zones, serving as origins and destinations of trips. Together, the data represents the user demand that will be traveling on the network. By understanding these patterns and different trip purposes, we can better predict demand and plan infrastructure that serves the community's needs. Network data. The second piece of the puzzle is what the transportation network looks like today and what is planned for the future. Network data includes information about transportation networks for all different ways to get around within a region. Travel demand models typically include roadway networks, rail, and bus systems. Bicycle and pedestrian network information may be included where available. Network data is typically comprised of nodes and links. It connects to the land use data through centroid connectors of TAZs. For the roadway network, characteristics like number of travel lanes, posted speeds, and facility type of each roadway segment are collected through a combination of aerial surveys and inventory of geographic information system data. For transit network, nodes and links are also included to represent transit routes and stop locations. Those data comprise a base year network for the model and provides important context for the travelers. Data sources for these inputs include U.S. Census Bureau Tigerline files, local GIS database, geospatial online mapping tool, or transit agency Google Transit feed. Travel data. Travel data offers information about all of the trips and activities on a transportation network. This information can be gathered by observing local traffic conditions or from a household travel survey. Traffic data is typically collected by local jurisdictions through sensors or cameras at intersections or roadways. These systems track vehicle speeds and the number of vehicles. Analyzing traffic conditions on a corridor or intersection can help identify bottlenecks and congestion. Household travel demand surveys are conducted on a random but representative sample of households. They collect information on an individual or family's mode of travel, trip purpose, and trip distance over a specific period. This information is critical to adjusting a model's population assumptions. To ensure a more accurate forecast, collected raw data must be processed to reflect a larger populace's information, aggregated and cleaned before being integrated into the travel demand model. Extrapolation. Some data inputs may need to be extrapolated as they are collected from a small sample. For example, modelers may extrapolate a household travel survey's reported data to a larger population. Aggregation and segmentation. Land use information and trip data are usually collected at fine granularity, such as at property parcel level, and often aggregated up to the TAZ level. In general, smaller TAZs provide a greater sensitivity for the model to reflect small-scale variations in the built environment and transportation system. Smaller TAZs can also better forecast accessibility for short-distance modes like walking and walking to transit, but finer-grained spatial detail requires higher level of input data and results in greater computational burden as well as longer model runtimes. Data cleaning. Whether the data is collected by FDOT or received from a partner agency, cleaning and verifying data is a critical last step before any analysis. Malfunctioning traffic sensors or batch process spatial data may require manual corrections. The data cleaning process includes checking for errors or inconsistencies, removing outliers, interpolating missing values, and adjusting the data to account for changes over time. Travel demand models only make predictions for the future. They can never guarantee 100% accuracy of what may occur. These models are built on historical data and assumptions about how people make travel decisions, which may not always reflect reality. Limited or poor quality data may lead to inaccuracy. For example, emerging technologies like driverless vehicles and high-speed rail are relatively new, which means there is not a lot of past data available to draw trends that can predict how people will use these modes in the future. User privacy. Travel demand models use aggregated, anonymized travel data to ensure user privacy. They reveal group travel patterns but not individual travel paths. Modeling travel demand is similar to predicting a hurricane's future path. The prediction is shown as a cone, which represents a range of areas the storm might affect. The wider the cone, the more uncertain the prediction. Likewise, the further into the future a model tries to predict, the less accurate the forecast becomes. It's important to remember that while travel demand models are useful tools, they should not be the only factor in transportation planning and decision-making. Travel demand models take complex data and help us to plan for the future, ensuring that our transportation investments support our current and future residents, visitors, and economy. To learn more about FDOT's forecasting efforts, explore the models, and access on-demand training, visit the Florida Transportation Forecasting Resource Hub at www.fdot.gov/forecasting.